Hello, this is lecture 10. I'm still doing velocity analysis. We started using vectors differentiating the loop closure equation in the last lecture. Okay, I wanted this lecture to start by just possibly emphasizing some definitions, and then I'll do some examples. All right, so this is my four-bar chain here in front of us, and again, I'm going to say I have four links, and this is my x-axis here. So this is my angle theta 2 as I measure from the positive x to the vector and right hand rule, and this here is parallel to x, so this is my theta 3, and this here is x, so it's parallel to that's then theta. This is theta 4, so I have my uh, three values which determine the position of the linkage, theta 2, theta 3, and theta 4. Now, my vectors R1, which is that's fixed length R1 angle 0, and R2 fixed length R2 angle theta 2, R3 fixed length R3 AJ theta 3, and R4 EJ theta 4. Now I wanted to say here that the difference, again, I'm just repeating something I said before. I want you people to be aware of. Like if I differentiated this vector R2 d R2 dt, this will give me omega 2 R2 a to j theta 2 plus 90, or pi over 2 if you like. This means this is a velocity term because it has omega now, omega times r, omega radians per second times meter, so that's meter per second, and the vector has rotated 90 degrees, as you can see. So the vector which represents the velocity of point A is perpendicular to R2. So I rotated R2 90 degrees type thing. So I can say this is VA, right? Then I can say R2 is really, I can call it RA if I want to, same, because it sort of gives me the position of point A with respect to the stationary point O2 or the origin type thing, and then it's an absolute position vector. Hence, when I differentiate an absolute position vector, I get an absolute velocity. So this here, this quantity here, this vector quantity is, or vector quantity is the velocity of point A, the absolute one. However, if I differentiated R3, I can look at it as RB relative to A. So that's relative position vector. Difference here is it relates point B to a moving point A. So both points move. Before, RA or R2 related the point A to a stationary point O2 type thing. So here, if I differentiated dr3 dt, and I get R3 omega 3 e to j theta 3 plus pi over 2. Again, it will give me a rotated vector like 90 degrees. So this means R3, or the relative position vector, will still be rotated 90 degrees type thing. And the value of this vector is R3 omega 3. However, this time around, this vector is only a relative position vector, does not give me the absolute or the real velocity of point B, just the velocity of point B from the point of view of an observer standing at point A over here type thing. Okay, so again, this relative position vector is still perpendicular as we agreed, because this is 90 degrees, right? So if I wanted the absolute position, the absolute velocity of point B, I can either add, I need to have I need to be able to have a vector which gives me point B with respect to a stationary point So it can be O2. So I can go to point B by saying like RB, I can say it's R2 plus R3 together. This will take me to point B, or R1 plus R4, and this also will take me to point B. So if I differentiated, if I added those two derivatives, so here if I want VB, it will be like I can then differentiate that, right? I can say then this will be omega 2 R2 A to J theta 2 plus pi over 2 plus R3 omega 3 E to J theta 3 plus pi over 2, which is equal to 0 derivative of this R1 plus R2 R4 omega 4 E to J theta 4 plus pi over 2, which is also, so either VB can be obtained from by adding those two vectors together, or just R4 omega 4 times this vector, which is E to J theta 4 plus pi over 2, which tells me now straight away that the velocity of B, so this is VB, which I get it by the sum as well, but easier to get it from this derivative, right? So this tells me straight away that the velocity of B is 90 degrees on R4, because we said 90 degrees. So it will be VB, the actual velocity of VB is 90 degrees to R4, right? Sort of thing. Now, but this, what we calculated before, when we differentiated V, when we differentiated R3, we got 90 degrees to R3, which was relative velocity. We were talking about the same point though, right? So this means the relative velocity is not the real velocity of the point, just apparent like velocity from the point of view of someone, and the absolute velocity, if you to get it, you have to relate the vector to a stationary point type thing. All right, so that's one thing I wanted to highlight to you. So we have real velocities in terms of point, in terms of point velocities, we have real velocities and we have relative velocities, right? Same thing applies to my angular velocities as well, so or link velocity. We can have real link velocity or relative link angular velocity. I will just explain this in a second as well. Now, I just wanted to say, all right, so if I have like in my that's my 4 by chain, I have this is link 2 and this is link 3, right? And so I have here, this will go to R3, this here is R2, and this is my angle theta 2, and this is my angle theta 3. All right, I measure it from X, correct? So now omega 2 is d theta 2 dt, omega 3 is d theta 3 dt, right? So both theta 2 and theta 3 are measured from the positive X. So that's measured from an absolute reference. So both are absolute angular velocities. They are both absolute angular velocities because they are the derivative of a quantity, like an angular distance, measured from an absolute reference, which was my x-axis. So they are both absolute angular velocities, right? So most of my angular velocities I get when we, in the way we do our analysis, we always measure all theta, theta 3, theta 2, theta 4, whatever theta, from the positive x direction and right hand rule type thing, like counterclockwise. And so all the thetas are measured from the same reference, and all the derivatives, all of them will give us absolute angular velocity. However, now if I wanted to have a relative, a relative angular velocity, what does this mean? So let's say if I extend link 2 a bit like that, so this angle here is from the same x-axis still, is my theta 2, and the difference, so now I have a difference here between link 2 and link 3, which is theta 2 minus theta 3, right? Okay, so now that's the difference, theta 2 minus theta 3. Okay, so theta 2, what does this represent? Theta 2 minus theta 3. Let's say theta 2 was 120, just give you like for example, that's 120, and this other value like theta 3 was like 90 degrees or something, right? So let's say it is theta 3 is 30 degrees or something like that. Okay, so the difference between them here would be like 90 degrees, right? Okay, so what this means that it's positive 90. So it means that an observer standing here in 3 will see theta 2 ahead by 90 degrees, right? Just giving you an example. It doesn't have to be 90, like can be any value during the rotational motion. But we'll see the difference. We'll see theta 2 ahead by this value. So, and hence, I'm just trying to say, I call this now theta 2 with respect to theta 3. So that's how I call it. Theta 2 with respect like to theta 3, or an observer is standing on link 3. All right. So now I have theta 2 relative to 3 is equal to theta 2 minus theta 3. All right. So normally when I number, I have, so whatever is written here first comes here first as well, and the second is second. And then this means, and the way I read it, theta 2 with respect to theta 3, or the angular position of link 2 with respect to an observer standing on link 3. Now, if I differentiated that, if I get d theta 2 to dt, that's d theta 2 dt minus d theta 3 dt, which means I have a relative angular velocity as well in my calculations if I want to calculate this value. So this is a relative angular velocity, right? So as was the difference between the absolute angular velocities I referred to previously up here on the page. So this here is omega 2, 3 is relative angular velocity, and this difference theta 2 relative to 3 is like a relative angular position, if you like, type thing. All right, so this is really more quite important when you study robotics, because normally the motors of the robot will be sitting at those junctions or the revolute joints between different links, and one end of the base of the motor will be fitted to a link, and the shaft will be fitted to another link, and then in this case those values will mean something to us. But in our analysis, if you design a linkage, you need also to use this value. And I'll explain what this means in a second. Like if this was link 2, so that's link number 2 over here, and around that's pin, around that I have link number 3, right? So this is link 3, and this is link number 2, right? So the difference, there is some angular difference, which is angular velocity, relative angular velocity, which is omega 2 minus omega 3. So that is rotating omega 2. This one is doing omega 3, right? Now we use this relative angular velocity to calculate something called the rubbing velocity. So that's because you have a pin here. This is a pin, and the pin has some radius like r pin or whatever sort of thing. So that's radius r pin. Okay. Okay. And this point here at the edge, like out on the pin surface, you have rubbing happening taking place between the two links because they don't have the same angular velocity. So if they have the same, then the difference will be zero, and now rubbing will occur. But you have some rubbing occurring, and then the rubbing velocity is equal to this radius r pin times the relative velocity equal r pin times omega 2, 3, or the relative velocity type thing. So that this is V rubbing, which will determine for me will give me some info on the endurance of the pin material and when you design the pin and whatever. So because the friction losses will also will be possible to calculate when you have this information besides as well the coefficient of friction and the pin. Okay, so so hence it's important to understand the concept of the relative velocity when you are designing a linkage, specifically when you want to calculate if you are actually want to make sure that the pin you have used is going to endure the stresses and whatever. All right, another thing I want to highlight here is the difference between a point velocity and a link velocity. The two different things we need to deal with in our analysis, and normally people like mix those and hence they get confused when they do the analysis. So our here, like go back to this example. This is R2 and R4, R3, right? Omega 3, omega 2, omega 4, right? Sort of thing. So now, then let's say I have a point attached here. This is A, B, C, any point anywhere, point D, whatever type thing. So difference between point velocity and link velocity. All right, link velocity is either omega or v sliding. All right, it's sliding velocity. Okay, let's say because sometimes v sliding is okay. We don't call it v sliding. Sometimes we call it like if I have a case like this one, it's still sliding velocity. I can say that's R2 and R3, and this distance is x, and this is point B, and it has some velocity here VB. This is the same, like this case, that's sliding velocity because the slider here sliding inside a cylinder or whatever, the piston sliding inside a cylinder or whatever. So that's still sliding velocity. And this V sliding, when I use it like that with a little s on top, it will be in the context of sliding on a rotating link type thing. So if I have this link rotating like that, so this distance, this is omega 2, this here is omega 4, and this distance r3, and it varies. This distance varies, which will create v sliding, right? V sliding is positive if r3 increases, and it is negative if R3 is decreasing. So you can tell when you get this value for Vs here, whether the slider is moving upwards to increase R3 or moving downwards to reduce it. So the sign of the velocity quantity in general indicates to me direction of motion type thing. All right. Okay. Same like omega. Omega is If it was positive, I know that link is turning anti-clockwise, counterclockwise. If it's negative, I know it's going in the clockwise direction because reducing the theta, which I always measure from positive x, right-hand rule, the counterclockwise. So those V sliding or omega are my link velocities, right? We call this link velocity. V slider is a slider velocity, and omega is a rotating link velocity. And when we do velocity analysis, we try to find link velocities, not point velocities. So velocity analysis is meant to find link velocities. Why? Because once I have found my link velocities, point velocities become, you can get them at minimum effort straight away. Once you have the omegas and you have different velocities of different links, you can just add, and like the example we did before, add like differentiate like R2, differentiate R3, add them together to get velocity of B, and so on. If you have your omega, it's so simple to do that. That's point velocity. Velocity always would be, you get it as vectors. So that's vectors, right? And so you know you need the direction of it. Specifically, if it was a random point, like point C here, point B, point D, point A, they change direction during rotation. So you need the velocity, the vectors, right? Type thing. So that's a vectorial quantity. The units for it is meter per second when you calculate the units for point velocity. And normally you get it after having done the velocity analysis. Velocity analysis, yeah. And after having obtained expressions or numerical values for your link velocities, you get the point velocity. So my velocity analysis is aimed at link velocities because simply once I have link velocities, I can find my point velocity as we did before. Like over here, example, if I want to find velocity of C, like we did in the last lecture, you can just have this vector here, RC relative to A, and you have this vector here, RA and R2, and you add them together. So VC, like RC, I need an expression for RC with respect to the stationary point, which is R2 plus RC relative to A, and then I differentiate those. VC is dr2 dt plus drca dt. And don't forget the derivative is so simple. We're not doing mathematics here. As simple as just saying dr2 dt is omega 2 r2 e to j theta 2 plus 90, and d rc relative to a dt is omega 3 because point C, this vector is part of link 3. So it rotates with it. It has the same angular velocity as link 3. So all links attached, all points, or well, link 3 or any link, right, can take, in reality, is not just a straight line. It can be a lamina, it can be any shape, right? So if I want to calculate any velocity of any point on it, I use omega 3. I just link this point with a vector to the pivot where link 3 is pivoted to other links, and I create a relative position vector there. And this relative position vector on this link will rotate with the angular velocity of the link. So RCA is a relative position vector for link number 3, so it will rotate with omega 3. So that's R, like the side here, the length is RCA or whatever, E to J theta 3 plus phi whatever plus pi over 2, because I'm saying maybe this here angle is equal to phi. So, and then when I calculate those, I add the two terms together, add the real terms together and the imaginary terms together. I end up with uh, like a vector quantity is still really imaginary. And if I wanted to have, so this will give me Vx, right? And Vx and Vy in terms of Vy multiplied by J type thing, if you like. And then if you wanted to have the actual or the, like the magnitude of this vector, you just square under square root and add under square root type thing. So that's another thing I wanted to say also. Now, another thing I wanted to say was the way I used my Kramer's rule, because I got some questions about that. Again, I'll just explain quickly how I used Kramer's rule in my analysis. Kramer's rule again is simply if I have a11 multiplied by x1 plus a12 multiplied by x2, that's equal to b1. And here I have a21 multiplied by x1 plus a22 multiplied by x2 is equal to b2. That's Kramer's rule. And if you remember how we used it, sort of if I wanted uh, x1, for example, oh yeah, okay, what we did was writing this equation in a matrix form. Okay, so over here, so I'm going to say in a matrix form, my equation is a11, a12, a21, a22 multiplied by x1, x2 equal to b1, b2, correct? And then I go so this determinant here is extremely important, because what the way I use it, I go here. This was a21. I'll just write this. Okay, clear. So now I go, if I want to x1, I divide by this determinant, a11, a12, a21, a22 here, right? And then I want x1, I write another determinant at the top and replace the column which corresponds to x1 by the column on the right hand side, b1, b2, a12, a22, and then this will give me a determinant over a determinant, and then again x2 will be similar underneath the same determinant, a11, a12, a21, a22, and but the determinant at the top is I replace, so a11, a21 are the same, but then the column which corresponds to x2 replace it by b1 and b2. All right, so that's this Kramer's rule as was given to us. Now, the way I use it is slightly different in kinematics, because I take normally okay, my equations are something like that. I have a11 ax1 plus a12 a, a12 x2, and then a21 x1 plus a22 x2, that's equal to b1 b2, but multiplied by maybe y or something like that. All right, it's multiplied by another y. In our case, this y corresponds to omega 2. All right, okay. So then when I use the method, I go x1, right, is equal to, again I keep a11, a12, a21, a22, and over here replace x1 by b1 y, and here b2 y, and here I have a12, a22. Okay, now so I have y appearing in this column here. This is y because it was on this side. Then I can take it outside as a common factor. So I can say, and you can do this when you calculate determinants, if the whole column is multiplied by something or whatever, you can take it as a common factor. So you go b1, b2, a12, a22 over A11, A12, here, A21, A22, right? So this multiply this by Y, all right? Okay, so the same thing, if you wanted X2, you'll end up with A11, A21, A12, A22. No, over here, I need to get rid of this and replace them by B1 and B2. And here I have Y taken as a common factor from here, right? Or divide this by A11, A12, A21, A22. All right, so this is my x1 and this is my x2. Y is a common factor. So I have three variables, albeit one of the variables is known, which is y, but appears as a common factor. So it comes out outside as a common factor. And hence I decided to give these determinants names, or these matrices that correspond to those determinants names, sort of thing. So I can call this matrix here. I decided to do this last time, so I decided to call this matrix, use a different color, this determinant, and this is coming from, this corresponds to x1, so I decided to call this jx1. All right, which I got it when I wanted to get x1. And it's really this matrix, you'll get it, as I said before, if you arrange your terms in the equation, arrange your terms around, transpose things around, but possibly it will be multiplied by negative because you'd have transposed things around the, around the equal sign type thing. So, but I'm not really worried much about the sign at this stage, type thing, right? So, but if you do that, okay, but we're not going to do that anyway. Now, so this, I decided to call this jx2 because I'm getting the value of x2. And then the one underneath corresponds to y because I get it when y is not, there's nothing really relevant to y in this matrix. And so I call this jy, right? So that's my jy determinant. That's my jy determinant. And you can tell now if jy is going to be equal to, just maybe here, if jy is going to be equal to 0, this will be a problem because I'll divide by 0, but it will tell me the only possibility for a system now using like linear algebra concepts, right? The only possibility, if jy as a determinant is equal to 0, if jy as a determinant is equal to 0, this one here, the only possibility for this system to have a physical meaning, right now let's use engineering terms instead of mathematical terms, for this system to have a physical meaning, if jy is equal to 0, this means like y will have to be equal to 0, right? Because you'll find in kinematics, most likely both terms B1 and B2 will not be equal to 0 at the same time as I referred to last time. So the y will be equal to 0 for the system to have a physical meaning. And this means if y is equal to 0, y is a velocity in our calculation. So this means the link has stopped, right? But if the link is not going to stop, like our intention that this link will keep running type thing for like continuous rotation, then this means if y is equal to 0, it's a disaster because this means the linkage will cease or will break or whatever type thing, because now the system will disintegrate, cannot be a physical system anymore, right? Same will apply to those other Jacobians on top. So if jx1 is equal to 0, x1 will be equal to 0. If jx2 is equal to 0, the x2 will be equal to 0. And in our case, this will be also, those will be velocities, and those, when we equate those Jacobians to zeros, will give us a like sort of the extreme positions of links. So I can, if you like, in kinematics, we can rearrange those equations to have them written in a nice and neat way. We can say like x1 on the Jacobian which corresponds to x1 is equal to y on the Jacobian that corresponds to y, which is equal to x2 on the Jacobian which corresponds to J to x2. The determinant of that. Well, I call them Jacobian in kinematics, but in linear algebra they are just matrices, right? Sort of thing. So don't confuse linear algebra uh, to kinematics. So like the determinant of the matrix, mathematicians will say, will call that. But these matrices will have more meaning to us as engineers than just abstract meaning in mathematics, because you will be more like coming from partial derivatives will be Jacobians. All right, so in any case, I can even write an expression like that to say, like to simplify my analysis and give myself a formula if I want to, right? So to use, if I want to use in things. So yeah, well, like the four-body chain, for example, if it was four-body chain or something like that, this is I had theta. Well, it was from memory was minus r2 omega 2 sine theta 2 minus r3 omega 3 sine theta 3. That's equal to minus r4 omega 4 sine theta 4, and then r2 omega 2 cosine theta 2 plus r3 omega 3 cosine theta 3 was r4 omega 4 cosine theta 4. If I arrange those to have r2 on the right hand side being, because link number 2 is my crank that's going to drive 360, like sort of complete rotations, I can arrange the equation r3 omega 3 sine theta 3 plus r4 omega 4 sine theta 4 being equal to r2 omega 2 sine theta 2, and then I will have r3 omega 3 cosine theta 3 minus r4 omega 4 cosine theta 4, that's equal to minus r2 omega 2 cosine theta 2. That's what we did last time. And I can then, I looked at my expressions, I discovered this r omega appear together. So I decided to use them together as if they were my x1 and x2 and y. So this here corresponds to y in what I just explained. This corresponds to x1 and this corresponds to x1 and this may be x2. This sort of thing. So now I have Jacobians, like I have Jacobians for theta 2, right? This matrix for theta 2, which has will be, if I decided to take those as common factors there, so I'll have minus or R3, R3 omega 3 is my x1. So inside the matrix, I'm left with sine minus sine theta 3, sine theta 4. I have here cosine theta 3 minus cosine theta 4 type thing. And then I have the other matrix, which is j theta 3, right? So now just imagine that you placed this column, the first column corresponds to theta 3 by the column over here, right? Which is sine theta 2, and here I have minus cosine theta 2, and here I have sine theta 4 and minus cosine theta 4, and then I have another matrix which is j theta 4. If I replace this theta 4 by the values on the right hand side, so I have minus sine theta 3, I have cosine theta 3, and here sine theta 2, sine theta 2, and then minus cosine theta 2, and then so these are my matrices. If I go back to this expression here, I want to repeat the same expression. I can say, okay, so this was x1, I put underneath j x1. Okay, so same thing here. So x1 corresponds to r3 omega 3, and I can put underneath then Jacobian j theta 3, but determinant, that's scalar quantity, and then over here I can go r2 omega 2, and determinant of that, which is j theta 2 determinant, and here I have r r4 omega 4 and j Jacobian j theta 4 determinant, and then I can equate those together to relate to get omega 4 as function of omega 2 and theta 2 whatever, and I can relate those together to get an expression for omega 3 as function of omega 2 and the other geometric parameters in the should be really theta 2 if I like, you know, if I have if I done proper position analysis, so everything else should be function of theta 2 every other angle. So this is a concept here that we can, this is how we use Kramer's rule. Last time I just used, I thought, well, like the thing which I didn't explain last time, that I can take a common factor from within the matrix when I'm calculating the determinant type thing from if the value is multiplied by a column or something. Let's do another example. Let's do another example. And this time around, I'm going to do the, before I do an example, let's just explain how to differentiate if theta, if the length of the vector is also a variable. So let's do that quickly. So if I have, so I have here, I have x and y, and I have a vector here, and then, right? So this is point A, right? Now, so this, well, I would say now this is the angle theta, and this slider. So the slider is moving on that, sliding on that. I'm going to call this VS, V sliding, and then so this here is R, up to here, that's R, and R is a variable. So R is actually a variable. Now, and I have the angle theta. Theta is also a variable. And this is what we did before. We just taken theta as a variable and we fixed R. And then if I go RA is R A J theta. A J theta, and both are variables. Now, if I want to differentiate that mathematically, it's as simple as saying, okay, I fix the first term, differentiate the second. So VA, fix R, differentiate theta, j theta with respect to t, which gives you, you know what this does? This straight away gives us, rotates, gives us omega, and rotates the vector by 90 degrees. This one will differentiate the e to j term. That's what we get, right? Okay, all right, so that's one thing. Over here, fix now e to j theta term, differentiate dr dt, and when I differentiate dr dt, I get a v sliding term. So now this will be equal to v sliding e to j theta. So now, because the sliding occurs on the direction of theta, like it's along theta, right? A to j theta, right? Doesn't change the not 90 degrees or anything like that. But this specific, this part, initial part, the first part of the derivative, when I differentiated the angle, I got the vector rotated by 90 degrees to give me this quantity as if the vector was constant in length. So this quantity here is equal to, this vector here is equal to r omega e to j theta plus pi over 2. So now, in this case, when the angle is variable and the length is variable, both vary, then what I get is the velocity of the slider in this case will actually encompass both velocities in it. So I'll get the slider doing both values. So I get the slider doing this vertical component with the link on which the rotation occurs and doing its own VS over and above that. So what will happen is I'll get the velocity of the slider will not be perpendicular to the link anymore, but will have both values added together here. So So this sort of thing. So that slider will have two contributions, its own sliding disk, the velocity Vs, and the contribution it gets from the frame on which the sliding occurs. And this frame rotates and imparts this rotate, the effect of this rotational motion to the slider as well. So this is what we get when we have a condition such as the velocity. So this here, the sum, this is the sliding over here. So this is the sum will be, I mean, this vector maybe change the color or something. Okay, this vector here will give me, this vector will give me the actual velocity of point A, right? It's just which combines both the sliding velocity and, so this is the sliding velocity here, right? So I'm going to say this here is a sliding velocity. Clean this bit here. So I'm going to say this is the term which goes, that's the sliding velocity term here, right? So I have, in this case, I have a sliding velocity term appearing in my calculations. All right. So if we quickly wanted to do an example, well, let's do this example now. Well, just I have over here, this is R2, this is R3, and this will be my distance X. So if I want vectors, this will be vector R2, this will be my vector R3, this will be my vector R1, right? And this is point A, point B. And if I wanted to introduce my vectors on the right hand side, as I systematically do, the length here is XB. Let's call this XB. And the angle is always 0, right? So the X direction. And then R2, the length is constant R2, and the angle is theta 2. And it varies, but R2 is constant. R3, small r3, that's constant length, and I have also theta 3 over here. So my loop closure equation is simply R2. I add those two together will be equal to the one that closes the vector that closes the loop. So R2 plus R3, that's equal to R1. And in polar form, R2 is equal to R2 A to J theta 2 plus R3, which is R3 A to J theta 3. That's equal to R1, which is XB A to J 0. And I differentiate this equation. When I differentiate the equation, I add here 90 degrees and I multiply by omega 2. And here I just add 90, theta 2 plus pi over 2 plus R3 omega 3, add 90 to this angle here, pi over 2. The other side, I differentiate both terms. Now, if we differentiate the first term, will give me VB, all right? And the second term and is still constant. And then I differentiate the second term, I'll get 0 because it's constant angle. I don't have to worry about it. Now, I can do my X, my real and imaginary. So real, from the real, I have R2 omega 2 minus sine theta 2 minus R3 omega 3 sine theta 3. That's equal to VB cosine 0, which is 1. So 1 times VB is VB. And then the imaginary term, I get it when I do the sine term. So R2 omega 2 and sine theta plus 90 will give me cosine theta. So this will give me cosine theta 2 plus R3 omega 3 cosine theta 3. It's equal to VB sine 0, which is 0. Then I can arrange my equation to have my known values on the right hand side. So I have here minus R3 omega 3 sine theta 3 minus VB equal to R2 omega 2 sine theta 2. And here I have R3 omega 3 cosine theta 3, and it's 0 here, nothing, and that's equal to minus R2 omega 2 cosine theta 2. And now I have exactly my what I had before. Like this is similar to my y in my analysis I did before. This is like x2, and this here is like r is like x1, r3 omega 3. And then I can have my I can say Jacobian j theta 2 as a matrix is just inside here. I will have minus sine theta 3 and minus 1, right? And okay, and then I have over here, maybe I just explain this quickly, do it in a matrix form, and then people would follow what I'm doing. So I'm going to say, okay, if I wanted to write an equation like a linear algebra, like a linear equation, I have my unknowns R3 omega 3, that's my x1, and VB is my x2. So inside here I'll have like a matrix, and then over here I'll have, so I'll take this as a common factor, R2 omega 2. This corresponds to y in my Cramer's rule when I explained it, and that here will be sine theta 2 over the first equation. This x1 is multiplied by minus sine theta 3, and VB is multiplied by negative 1. Okay, and the second equation, R3 omega 3, which is x1, is multiplied by cosine theta 2, cosine theta 3, and VB is multiplied by 0. The other side I have minus cosine theta 2. And this here was my, this is my Jacobian j theta 2, which I do it when theta 2 is on the right hand side. So j theta 2 is what I did before, is this matrix minus sine theta 3 minus 1 cosine theta 3 0. How about j theta 3, this matrix? Then I replace here by, I replace the first column by sine theta 2 minus cosine theta 2, and I leave the other column as is. Then how about V j xb, because this corresponds to the distance xb. I keep the first column as it is, minus sine theta 3 over here. This is j theta 2, and then over here that's cosine theta 3. On the other side here, instead of VB, the VB column will be replaced by the column on the right hand side, which is sine theta 2 minus cosine theta 2. All right, so now I have those ones. The determinant of every one of those we can calculate on the side here. J theta 2 as a determinant is multiply those, start from the top leftmost term, and then minus, so minus that. So we'll get cosine theta 3, and from here the determinant of this matrix is just equal to minus cosine theta 2, and then the determinant of this matrix, the jxb. Okay, just maybe writing. So determinant jxb is equal to, multiply those together. All right, we'll do it on another line, I guess. So I'll just do it on another line here. Okay, now I'll get it here by saying determine jxb is equal to, multiply those together, you get sine theta 3 cosine theta 2 minus cosine theta 3 sine theta 2, which is sine the difference between 3 and 2. So this is this Jacobian. Now if I want to apply the rule which goes omega 2, like like the y over jy, remember the determinant of jy, y was r2 omega 2 over the determinant j theta 2 is equal to omega 3 r3 over the determinant of j theta 3 is equal to R4, or no, I don't have R4. I have over here VB over the determinant of JXB, and this way I can calculate my velocities. So if I wanted omega 3, so omega 3 is equal to, don't forget that every determinant underneath is important because it determines for me whether the vector is like the specific variable at the top is going to be equal to 0, right? Type thing. So when the one is really of like it's really of great importance is the one under omega 2, because I hope that this omega 2 is going to be continuous, not going to be equal to 0. Then j theta 2 should never be equal to 0. And then when I go determinant of that, this means cosine theta 3, this determinant j theta 2 is equal to cosine theta 3, and this tells me cosine theta 3 can never be equal to 90 and all the multiple of that, because cosine 90 and multiple of 90 is equal to 0. So this tells me that if link number 3 is going to be vertical or allowed to be vertical, the linkage is going to cease at this point in time, and because this means omega 2 will have to be equal to 0. And then so you can tell if j, I can possibly write a note j theta 2, this determinant j theta 2 was equal to cosine theta 3, and the mobility information I get from there is this. So if this is going to happen, this R2 and R3, if this is going to happen, this means here omega 2 will have to be equal to 0, right? And the linkage stalls. Linkage stalls at this point in time. And so, and this will happen if R2, of course, we looked at this before, if R2 is greater, and then we can look at the conditions which will make this happen, and then we can tell if R2 is greater than R3, this is going to happen. So you can also, if you want to look at j theta 3 over here, which is minus cosine theta 2, then and then tells you when omega 3 is equal to 0, this means when cosine theta 2 is equal to 0. This means theta 2 is 90 or multiple of 90, because this exactly. So this the crank is rotating, no problem. That's linkage not storing. So I'll just j theta 3 was equal to minus cosine theta 2 or something like that, wasn't it? Okay. So all right. So I hope that's okay mathematically. All right. Maybe all right. Okay. In any case, we can say this will happen when this is the situation, and makes sense, right? So if the crank is like that, this is 90, or like multiple of 90, then this is omega 3 is equal to 0. At this point also, omega 3 is equal to 0. The con rod is not going to go any higher or lower than this. This is if theta 2 is equal to pi over 2, 3 pi over 2, whatever multiple of that, then omega 3 is going to be equal to 0. And this makes sense. What about the other one, JXB, this slider here? So, which is sine the difference, JXB, which is sine theta 3 minus theta 2. That's equal to 0 if theta 3 and theta 2 are equal, or like the difference between them is 90, and this is 0, and this will happen when the crank is horizontal like that. So this is one possibility. So this is here R3 comes on top of R2 type thing, and so the difference between them is 1. So the difference between them now is like 180 or something, and the other one is, so here the difference theta 3 minus theta 2 is pi, and the other possibility is that R2 R3, so this is R2 and this is R3, and over here, so here theta 2, theta 3 minus theta 2 is equal to 0. And that both over here, like VB is equal to 0, VB is equal to 0. I get this from the Jacobian. And they refer to this as the mobility analysis. That's mobility analysis. So we use the Jacobian, this Jacobian representation to conduct some nice mobility analysis for the linkage. And if you go back here, if you want to calculate your omega 3 or VB, it's just a simple, it's really simple substitution. Like if you wanted omega 3, it was here or like or R2 over R3, omega 2 multiplied by, here I have J theta 2 over here with J theta 3. Just like substitute these values to get the expression, and VB was R2 omega 2 over J theta 2 determinant over here JXB determinant. This calculate this expression will get, it's easy to calculate. And what you can just really realize here as an engineer is when you calculate omega 3, you get the same units as omega 2 because you have R2 over R3. That's like like the units cancel out, the length units cancel out. When you calculate VB, you get VBR multiplied by omega, which is gives you meter per second, and this gives you radians per second. So you make sure when you check your units, you make sure you have done the right thing and you have at least an expression that makes sense. Okay, thanks for that, and we'll do more velocity analysis in the next lecture. Okay, bye for now.